Welcome to Lab 1. This is an overview of the labs for the first half of the semester. We have 4 labs altogether, Lab 1, 2, 3 and 4. And throughout these labs we'll take you through all the content you'll need to complete Assignment 1. Do note that Assignment 1 Part A is due after Lab 1, and we also have a help session for Assignment 1 Part B. In Lab 1, we are going to take you through FPGAs, or Field Programmable Gate Arrays. We are then looking at the component hexadecimal to 7-segment display, which is a decoder for your visual output of a number on your 7-segment displays. And we're going to round it up with the tasks that are expected to be done by the end of Lab 1. A simple programmable logic device consists of a number of AND or OR gates with electrically programmable junctions. Now, these AND and OR gates are logic gates. If you remember from the lectures, they provide logic functions to the signals. A logic circuit can be implemented by fusing the desired input signals to the inputs of the logic gates. So as you can see in the picture below, the junction fuse remains intact to make the connection, and then you have a multiple input AND gate to give your output. These outputs are Boolean expressions. So in this example, the output is A, B bar. So it is A and not B. Programmable logic can then be extended into programmable logic arrays, as you can see here. Now, instead of just having multiple input AND gates, the outputs are based on AND gates and OR gates. So the gates just before your outputs down here are OR gates, and these along here are your AND gates. These can then further be condensed into programmable array logic, or PAL. Generally speaking, a FPGA is made up of a lot of these programmable array logics, which you will design yourself in this subject. And they basically consist of these junctions which are fixed. Field Programmable Gate Array. These are colloquially known as FPGAs. FPGAs contain an array of programmable logic blocks and a hierarchy of reconfigurable interconnects that allow the blocks to be wired together. So if you can see these 2 images down at the bottom, you individually design these logic blocks and program them, and then as you are translating your program into the chip itself, these connections, so these interconnection resources, then start happening to wire the different logic blocks together. And these all interface with whatever hardware you have through these input-output cells. Now, each one of these logic blocks includes memory elements, which may be as simple flip-flops, or even just your basic programmable logic circuits, or it consist of more complete blocks of memory. There are multiple advantages of field programmable gate arrays. Just to list a few of them, you can see in this slide. Predominantly, they are very low power. They have very low power consumption. They allow for large number of logic gates, RAM, register counters, and routing resources. It's a great chip to use for fast turnaround prototyping due to the ease and the versatility of programming FPGAs, and most importantly, they are reusable, which means if you go to a different project, you can reuse these chips in that project as well. In FPGA, the program design flow is as such. You start off with your specifications. So these are the graphical schematics that you draw up, or the VHDL codes that you write. These are all designed by you or whoever the programmer is. They need to be synthesized by the software. Once they're synthesized, there needs to be a verification. This step is usually best practice. There's a functional simulation, which means you can simulate the outputs based on a hypothetical input that you are inputting. This simulation can be done through software or hardware. Generally, it depends on the project and what type of programming you are doing to determine which way would be better. In implementation, you have translation, fitting, and program file generation. So translation, as we mentioned before, is where the interconnecting resources get to work and they start wiring the junctions together, they're wiring the logic blocks together. And fitting also is part of that process where all the inputs-output cells are then connected together to your logic blocks to give your interface outputs. Program file generation is then the generation of the bit file. So for FPGAs, they produce bit files which can then be uploaded or downloaded into your chip or on a flash memory, which then loads onto your FPGA chip. And as you can see down there, system debug is programming the design on the target device. If you can see the image on the right here, this is a basic flowchart giving you some ideas of this program design flow. Now in the FPGA, then always needs to be a voltage going through every pin. If a pin is not connected to any voltage source, it is called a floating input. This is also the case for most chips and processors, where each pin will require a voltage going through it. And the reason we don't want any floating inputs is because they can register as a high or low logic, which can cause unpredictable behavior in an application. Now we're going to look at active high versus active low. If you look at the image, this is an example of an active high logic. As you can see, going through pin 1, you have a resistor, which is 1000 ohms or 1K0, which is also connected with a switch to a 3V 3 source. When the switch is on, so when the contacts are touching, the current, the voltage going into pin 1 would be high, since the 3.3 volts voltage source would connect to the inputs. When the switch is off, you can see that the voltage of pin 1 would be 0, since your ground is connected to pin 1 through the 1K0 resistor. This resistor that you use is usually called a pull down resistor or a pull up resistor. You'll see, as you can see in this image. So in an active low situation, in an active low circuit, you can see that when the switch is off, it is high, and when you switch the switch on, it becomes low. Thus the naming convention: active high, active low. When in active high, when the contacts are closed, your pin would have a high logic, whilst in active low, when the contacts are closed, you have a low logic. Now, for more information about the FPGAs that we are using for the MXK, the FPGA we're currently using is the Xilinx Spartan 6 with HEX2SSD. There are links to these two data sheets, one for the Spartan 6 family overview and the other one specifically for the FPGA data sheet. They are worth looking into for more clarification or more information regarding the FPGAs itself, such as how many pins there are available, what are the modules that are available for you to use, and so forth. on your MXK boards, there are 6 7-segment displays. These are LEDs, which can display a number or a letter. As you can see in the image, there are 7 segments to display the number or letter. As you can see, there's A, B, C, D, E, F, G. And in our case, in our specific model, there is a pseudo 8th segment, or an 8th segment called decimal point, as you can see as DP. And a number is displayed on the 7-segment display through switching on the corresponding segments. So for example, to display the number 1 on your 7-segment display, segments B and C are turned on. As you can see, that is, if you can see the mouse clicker, that's segment A, segment B, segment C, D, E, F, and G. So to display the number 1 on your 7-segment display, the segments B and C needs to be turned on. Now, in order to show all available numbers that you can show in the 7-segment display, a decoder is required to decode the number to display on the output. So, as you can see in this truth table, the number 0 requires segments A to F to be switched on, except for segment G. And as we were saying before, segment for the nut showing the number 1, segments B and C have to be on. And another example is if you want to display the number 8, all 7 segments have to be switched on, as you can see in this logic of 1s and 0s. Now the input, the output that we want, the output that we want can be encoded into 4 bits, as known as a hexadecimal input. So in order to output the number 0, the 4-bit input is 0, 0, 0, 0, and this goes up in binary fashion, so that to show the number 1, the input should be 0, 0, 0, 1. To show number 2 should be 0, 0, 1, 0, and so on, until you reach F, which is 1, 1, 1, 1. So this is the table to encode each of the output numbers we want into a hexadecimal input into our HEX2SSD. Now let's take the example of segment A. From that truth table, as you can see on your left here, to show numbers from 0 to F, you have your 4-bit inputs for each one of those numbers that you want to output, and for each one of those outputs, segment A needs to be switched on or off in order to achieve that number. Now, from this column of seg A, you can see the truth table for segment A. Now you need to then derive the Kana map or the K map from this truth table. As you can see in the example in the picture on your right, you can see that it's been encoded in W, X, Y, and Z, and each corresponding output for segment A is then filled into the K maps. Refer to the lecture videos for K maps to learn more about deriving the K maps, and as well as that, do refer to the lectures videos as well in order to gain more information about deriving the Boolean expression. Now in our specific example of segment A, from the K map we derived before on the left, we now need to group the ones together in order to gain a Boolean expression, as you can see down in the bottom over here. Now do refer to the other video giving you an example of using Xilinx ISE design suite to design and program your own schematics for this segment. For Lab 1 tasks, the main component we expect you to achieve is the HEX2SSD, or the hexadecimal to 7-segment display. Now, in order to extend what we've shown you in this video, you need to draw out the K-maps for all 7 segments and then obtain the Boolean expressions for each of them. You are then to design or draw the schematics for each of these segments and group them together into the decoder as HEX2SSD. And once that's done, you will then need to simulate this HEX2SSD in Xilinx using the VHDL test benchmark in order to finish assignment 1 part A. There are a few references available on UTS Online, specifically the PDF file for programmable design logic tutorial on synthesis and simulation. Do have a look through that, as that will help you in your simulation. As well as that, there are lecture videos that you should refer to if you have any issues with understanding the content, specifically deriving the K-maps and the Boolean expressions from a truth table.